Okay, why don't we get started? Before we settle in on lecture, why don't we have a little bit of time to talk administrivia for next week's midterm 1, yeah? So it's a week from today, Thursday. It's going to be in class, or at least during class time. But because we don't all fit in this room, there's actually going to be an overflow room announced on Piazza. I forget where it is, but it's been 101 Morgan. And a policy for which room you're going to be sent to will be posted on Piazza. We're going to hash partition you into 2 partitions. None of you will spill, I hope. Actually, there's also, for those of you who have DSP accommodations, there will be a 3rd room, which is, I think, it's in Soda Hall. I think it's 380. I don't know if I've passed that one out, but there will be a room for people with DSP accommodations. There will be a TA or a faculty member in all of these locations. We will also have a shared Google Doc which will project on the screen with any questions or modifications that everybody should need to know about. So we'll have kind of a shared whiteboard. You're allowed to have a cheat sheet. All right? And here's my philosophy on cheat sheets. I'm not a big fan of memorization exercises. I don't think they're important, and I'm pretty bad at them anyway, so I hate to inflict them on you. The reason to make you have a cheat sheet is just really, it's a form of data reduction, all right? It's a study guide. So if you go to the trouble of distilling all the information you've learned over the past 8 weeks, I guess it's been maybe, into one piece of paper, that's studying, okay? That's good use of your time. And also, it's been shown many times in studies that if you write it by hand, it goes into your memory better. All right, so one thing you can do with this sheet of paper is take all the slides, print them real small, and put them on one sheet of paper. And then you know what happens during the exam. You're doing a nested loops join between the questions and the content, right? You want to construct an index of the information. You want the information to be aggregated to a conceptual level that's meaningful, right? And you want to make sure to keep in cache, so to speak, those things that you're likely to need or that you can't keep up here, right? So that exercise of figuring out what you want to write down so that you do well in the exam, that's called studying. All right, you can call it cheating if you want to. That's fine with me. All right. So do with it what you will. If you want to embed the entire textbook into the molecules of this one sheet of paper, go for it. That's fine. I don't care if you write on the front, the back, in between, anything you want with this one sheet of paper. My goal really is to get you to distill. Okay. So you can copy your friend's cheat sheet, but that won't do you a damn bit of good. Really. You should generate your own. You can do them in a group. That's fine. But that writing down process, that distilling process, I call it studying. Okay? It's just a forcing function. So you get a cheat sheet. Somebody very wisely asked on Piazza, what about midterm 2 and midterm 3? Can I reuse my cheat sheet? I think what I'm going to do is a little bit of forcing you to distill again. So midterm 2, you'll also get one piece of paper. Mostly different content. And then for the final, we'll have to decide if it's 2 sheets of paper or 1 sheet of paper. It might be good to make it 1 because then you'll distill one more time, but maybe we'll let you have the final on 2. In any case, assume you have 1 cheat sheet for the midterm 2 as well. All right, and there is some cumulative material, so that'll kind of keep you moving along and compressing as you go. Any other logistics questions about the midterm? The cheat sheet should be 8.5 by 11. Okay, I think that's it. If you have questions, don't hesitate to post them to Piazza. Thank you. There is a review session Sunday. I think it's 2 to 4. Is that right? And I forget the room. Do you remember the room? 2050 VLSB. Valley Life Sciences. Okay? The TAs are going to run it. They're going to work through the last time I taught the class, midterm questions. All right? So you'll get a good pattern match to the kinds of questions I like to ask. You will get the questions they're going to go over in advance. So you can prepare to come with focused questions at that session. You may want to think a little outside the box of those questions and ask things about, well, what if the question were different in the following ways, right? Because each year the midterm can only hit so much stuff. Okay? But it's not going to be just a walkthrough of the slides. It's going to be kind of problem-oriented. Any other thoughts from the TA team here? Yeah, so I'll just emphasize, look at those midterm questions that are being passed out on Piazza or the website before you come, so that we're not just doing a recitation on Sunday, but these guys are actually helping you work through the questions that you have. Often good to hear other people's questions too, so even if you think you know it, it may well be worth hanging out. Any other logistics questions about the midterm? I know this is coming fast and furious because homework 3 is due tomorrow night, not tonight, but tomorrow night. So you're busy with that, but should give you some time, at least between Friday and Sunday, to prepare for a review session, and then you'll have all next week to actually work on preparing for the exam. I wanted to show you something from today's Daily Cal. I don't think it came through, though, on my email. I only have it on my iPhone, so we'll just have to wait and see if that comes later. Okay. So be it. All right, so meanwhile, back in database land. Oh, there's my calendar. That's exciting. Yeah, I know. It's a bummer. Okay. Here we were. Last time we were talking about entity relationship modeling is where we left off, and we'll start back from the beginning of that section. So we begin with the notion of entities, which are individual objects in the world, sort of like nouns. They have attributes. And then entity sets, which are collections of objects with the same attributes. Okay, so similar entities. The picture at the top is a graphical depiction of the entity set employees. It's got an attribute SSN, which is a key, and you can tell that because it's underlined. And it's got 2 other attributes, name and lot. You can have a multi-attribute key, just like in the relational model. So you can have first name and last name. Both of them underlined means they're a composite key. Okay? So those are entity sets. And then we have relationship sets, which annoyingly fly into the slide as if it's 1998. Sorry about that. It's kind of yucky design. Works in is a relationship set. A relationship set is a set of relationships between individual entities. So works in is a relationship between an employee and a department. Bob works in the shoe department. Works in the relationship set relates a set of entities with a set of departments. And we'll talk about next kind of the different flavors of relationships that we can have. But note that relationships themselves can have attributes. So in this example, the works in relationship set has a since attribute because each employee has worked in a department since a particular date. Okay? We talk about relationship sets having an arity, which is the number of entity sets that they combine. They don't have to be binary. We'll see examples of ternary entity sets for sure in a slide or two. Any questions on the basics of entities and relationships, or entity sets and relationship sets? This graphical depiction is actually the language in which we will program this idea, or at least if you get a modeling tool like ERWin, which is a sort of standard desktop modeling tool that a lot of people use. There's nothing special about it, I wouldn't say, but it's a canvas, and you drag boxes and diamonds and arrows, and you build up your data model in that visual language, okay? It's perfectly formal language. And we'll talk about the shapes of these edges in this graph shortly, because they can change. Yes? Can I go back one slide? You bet. The question is something I talked about last time, but not this time. Each attribute has a domain. Think of that as a type. Okay, so the domain might be integers or floats. In principle, the domain could be anything. So you could, in theory, have a domain like companies registered with the Federal Tax Commission, right? And maybe that's a domain you know about off the top of your head. Or you could have a domain that's defined by a regular expression, strings that match this regular expression. We're not going to worry about that here. Just think of it for now as data types. Okay? Domain is a finite or infinite set of legal values. It's really a constraint, an integrity constraint. Make sense? Okay. Other questions about the basics? It's good to get the basics right. All right. So, just like you can have self-joins in the relational model, you can have cases where in an ER diagram, the same entity set can participate in multiple relationship sets or in different roles in the same relationship set. So here's a case where employees participate in the works-in relationship set. That's fine. Employees also participate in the reports-to relationship set, and they participate in two ways because they're on both. They have two edges going into that relationship set. And we might want to label them, the different roles that the employees play. There's the supervisor role and the subordinate role in a reports-to relationship, right? So an employee manages an employee, but sometimes the relationship set is playing the role of the supervisor, and sometimes it's playing the role of the subordinate. It's as if you're doing sort of a self-join there, if you want to think of it in those terms, right? Managers and employees. They're all employees, but we have this relationship set that arranges them in this way. Okay, so Michael Franklin is the chair. You met him. He is the supervisor of me, right? We are both computer science professors. Similar deal. All right. Questions? All right. Key constraints. So we talked about keys, but now we're going to talk about key constraints as they relate to relationship sets. So we talked about keys of entity sets. Now let's talk about key constraints in relationship sets. This diagram says, which just has plain old, those red edges are just emphasizing the fact that these are undirected edges in the graph. They're just plain old undirected edges in the graph. And what they're indicating is that there's no integrity constraints, no key constraints on those relationships and the way that the entities participate in them. So an employee could work in 0, 1, 2, any number of departments. And a department can have 0, 1, 2, any number of employees. We call this a many-to-many relationship. Now, the manages relationship, we probably don't want that. We probably, well, maybe in our organization, we don't want someone to have two managers. Or maybe we want everybody to have at least one manager. So there's different things we can say here. So if we draw a directed edge from an entity set to a relationship set, what we're saying is that that entity set has at most one participation in that relationship set. So what we're saying here is each department has at most one employee who manages it. The department participates in manages at most once. Did I say at least once the first time? I meant at most once. I hope I said it right. All right. So if you see that arrow, the way you can think about it is sort of visually, there's a way to go from a given department to a particular employee that manages it. There can't be two. All right. There can be at most one. All right, so that's a greater than one. So let's write that down because we're going to need this later. If we have a picture like that, this is less than or equal to 1. At most one participation of this guy in the relationship set. All right, we call that a key constraint. All right. So here's a picture of a many-to-many relationship between two sets. The sets are being depicted as ovals. The entities in the sets are being depicted as black circles. The relationship is the relationship set is the graph that connects them. So each relationship is the edge between two entities. All right, and you can see that this is many-to-many. There's things on the left that have many matches on the right. There's things on the right that have many matches on the left. Yeah? So that's a simple way to picture that. Here's an example of a one-to-many relationship set where things on the right have at most one thing on the left. All right, things on the left can have many things on the right. And there's cases in this where you could have an item on the left or the right that has no participation in the relationship. Here's an example of a one-to-one relationship set, right, where you have at most one match from the left to the right, at most one match from the right to the left. We haven't seen one of those yet, but we will. Now, in addition to the key constraints on relationship sets, we can also have participation constraints. So a question like, we want every employee to work in some department. So every employee must participate in the works-in relationship set. Okay? And to do that, what we'll do is we'll draw these thick edges. All right? That's the graphical language we'll have. So a thick edge between an entity set and a relationship set means greater than or equal to 1, participation. Every item here participates at least once in the relationship set. Right, so it's called a participation constraint. And if we have this, we'll say that the participation of, in this example, employees in the works-in relation is total. That is to say, there is a participation constraint. So it's at least 1. Questions? All right. We might also say that every department has at least 1 employee. That seems like a reasonable thing to say. And here, what we've done is we've got an arrow that is both thick and an arrow. All right. So if you take the conjunction of this predicate and this predicate, you have equals 1, right? Greater than or equal to 1 and less than or equal to 1 means equals 1. So if you have something that looks like that, fat arrow with an arrowhead going into a relationship set, that by definition is equals 1 because it's greater than or equal to 1 and less than or equal to 1. Okay? So you can have that as well. And what this is now saying is each department has exactly 1 manager. We used to be saying each department had at least 1 manager. Now we're saying at most 1 manager. Now we're saying each department has exactly 1 manager. Right? The arrow is at most 1. The fattening is at least 1. The combination is exactly 1. All right. This is the notation, the graphical notation used in the book, arrowheads and thick edges. There's an alternative notation that's used in some of these tools, I think including ERWin, which is called crow's foot notation. If you want, you can look at this. It's another way of marking how things could be 1 to many, 1 to 1, or 0. So participation would be a 1, and key constraints are 2, 1. So anyway, you can look at this example if you want. We will not test you on this. I just wanted you to know that this exists and have seen it. But the notation we'll be describing and talking about in class will be the notation in the book, which is the arrows and the thick edges. Okay, I just sort of threw this in as informational because you'll see it in tools out in the field sometimes. Okay, so this is all pretty straightforward. So the summary so far, just to make sure you got entities collected in entity sets, we draw those as rectangles. Relationships and relationship sets, we draw as diamonds. Key constraints, which means at most 1, we draw as arrows. Participation constraints, at least 1, we draw as bold. All right? And that's enough to get started. All right? And that's usually a pretty useful thing to write down when you're modeling something in the real world. And we'll show you how to translate this into SQL integrity constraints in a little bit. But this isn't necessarily everything we want to capture, and the ER model has more richness to it. So let's keep going forward with this stuff. The next thing we'll talk about are what are called weak entities. All right? And the idea is that a weak entity is something it doesn't fully have identity. It belongs to something intrinsic in your data. It itself is not. So this weak identity can be identified uniquely only by considering the primary key of another owner entity. And rather than read this through, let me give you an example, and then we'll come back to the definition. So here's an example from sort of insurance. All right, there are dependents, there are employees, and there's a relationship between them, which is that the dependent is covered by the employee's insurance policy. All right, so my daughter, one of my daughter's name is Dahlia. Dahlia is in the database. She has a name, Dahlia. She has an age, 10, okay? But she doesn't have a unique ID. She's not an employee of the University of California. She doesn't even necessarily have a unique ID in my insurance carrier. The insurance carrier's ID for her is me. It's my ID, and then there's a dependent, Dahlia, who is covered by my policy. So to identify her from all the other Dahlias in the world, you need my social security number and her name. Her name distinguishes her from the rest of my family, right? But my ID distinguishes her from the rest of the employees and their children. Make sense? So that's called a weak entity. And the way we draw a weak entity is we bold out both the entity set, well, all three of the entity set, the relationship, and the relationship set. All right? Now, why is the relationship set a bold arrow in this case of a weak entity? Because we want to make sure that every dependent has exactly one employee they're associated with. So suppose that my spouse worked at the university. Dahlia would have to be covered by my policy or by her policy. She's not allowed to be covered by both. Right? And she's not allowed to be covered by nobody and be in the database. Right? She has to be covered by exactly one of us. So the exactly one, the key constraint says it's at most one. The participation constraint, the boldness, says it's at least one. Right? So weak entities, by definition, need to have these bold arrows into their relationship. And the way we identify that they're weak entities is that there's an identifying entity set over here, and this underline, dotted underline on P name, that's called the partial key of the weak entity set. And the full key of the weak entity set is my key concatenated with that partial key. Okay? So to go back to pretty much everything I just said is what all the description above is. There's an owner entity set and the weak entity set. They participate in a one-to-many relationship set. One owner, many weak entities. Right? And the weak entity must have total participation, which is boldness, in the identifying relationship set. Okay? And I think we covered everything. All right, this example is a good one to keep you focused. And the weak entities have only a partial key, which is that dashed underline. Okay, so I taught you some different ways to model some stuff, but now we have to kind of put it into use. And it can be actually surprisingly subtle and confusing what the meanings are of different ways of describing things. So let's think about binary, two-way relationships versus ternary, three-way relationships. All right? We have employees and we have dependents with weak entities, like we saw before, and we have insurance policies. Okay? So suppose that each policy is owned by just one employee. All right, so we're not going to worry about married or we're not going to worry about partners covered by the same policy. Each policy is going to be owned by just one employee. All right? Then we might connect this up in a ternary relationship on covers, where you say that each policy has at most one employee associated with it. Okay? And that employee could have many dependents. So that key constraint on policy means that there's at most one employee. But it also, unfortunately, means you can have at most one dependent on here because the policy can participate here only once. So I actually do have two daughters, but because policy participates in the relationship set covers only once, the coverage of one daughter would be what the policy is about. All right, so with this ternary relationship makes that key constraint for policy apply to both employees and dependents. So that policy is associated with at most one dependent as well as with most one employee. So it's probably not what we want. Okay? Make sense? One more time. The key constraint from policy says that policies participates at most once in the relationship set, and the relationship set covers both dependents and employees. So the policy is associated with at most one pair, employee and dependent. Right, which seems like a bummer because then I can only have that policy for one of my kids. So what we might want instead is two binary relationships rather than a ternary relationship. We're going to introduce another relationship set, or two different relationship sets. One is the beneficiary relationship set, which connects dependents to policies, not to employees. So now Dahlia's on a particular insurance policy. She's not with a particular person. And then each insurance policy belongs to exactly one employee. Make sense? And now we can have multiple dependents on the policy. We can have exactly one policy per employee. Right? To be clear, one more time, policies to dependents is one to many. Right? Each policy can have many dependents. Each dependent is on exactly one policy. So it's many. It's many to one. Right? And then here again, let's get this right. Each policy belongs to exactly one employee. In principle here, an employee can have multiple policies, which is okay, I guess. Maybe you want to forbid that, maybe you don't, but in this schema, it's allowed. All right, so that's probably a better design. So you should definitely think through each one of the edges in this diagram and each one of the edges in the previous diagram and make sure you understand exactly what they're preventing. This is all about constraints. It's all about everything could be many to many. 0 or more on each side of the relationship. You want to think through, what are we forbidding? What are we constraining? By putting in bold edges, by putting in arrows, by putting in weak entities. All right? So think through each one of these. There's a lot going on in this lower diagram, even though it's small, and you should make sure you understand each implication, the implication of each design decision for each edge. Okay, so we've seen an example where a ternary relationship was a bad thing, and two binary relationships were a good thing. You'd expect that I would show you an example the other way around now, right? Where a ternary relationship is a good thing, but two binary relationships will be the wrong thing. So let's go through that. Okay. Oh, I just said what's in the slides. So here's an example in the other direction. We got contracts, we got parts, the contracts connecting parts, departments, and suppliers. All right. Let's just go through it. So there's quantities on these contracts. So let's look at the top ternary relationship. A contract is a connection between some particular parts we want to buy, particular suppliers of those parts, and particular departments that are presumably paying or responsible for this contract. Okay? So in the top, the contract covers all three of these cases. Let's look at an alternative design with two binary relationships, or actually three binary relationships. Suppliers deal with departments. Departments deal with suppliers. Parts are needed by departments, and departments need parts. Okay? And suppliers can supply parts, and parts can be supplied by suppliers. And that's all fine. The question is, when you have a particular contract, where does the quantity go in this lower diagram? How do we say that, the shoe department needs 2 shoelaces from, Bob's shoelaces? Right. Where do you put 2 shoelaces in this picture? We know that Bob can supply lots of shoelaces, but if we put the quantity there, that represents how many shoelaces Bob's could possibly supply, not how many are on this particular contract, right? So it's not at all clear where to put quantity, and in fact, there is no place to put quantity here that would have the same semantics as it does up at the top. Okay, so that ternary relationship is kind of what we want in this case. It is what we want in this case. Again, this is one of these things, I can say it, you can look at it, you sort of get it. But if you don't sit here and review it and think about some examples of the data you want to model, you probably won't absorb it. So with all these things, I strongly encourage you to go back, stare at every relationship, and ask yourself why it's the way it is. Okay? All right. There's a notion in the ER modeling called aggregation, which is different than SQL aggregation. SQL aggregation is about taking a bunch of numbers and computing a statistic. This is about taking a bunch of entities and relationships and kind of wrapping them up as if they're like a big encapsulated entity set. Okay? So let's see how this works. The idea is roughly to allow us to have relationships between relationships by treating these as entities. But you'll see what I mean in a minute. It's really a form of encapsulation. So here's this thing we looked at earlier. I think we did, maybe not. We have departments and we have projects. And the departments are going to sponsor projects, okay? Projects have a project ID, a start date, and a budget, the P budget. Departments have a department ID, a name, and a departmental budget, which is just called budget. Okay? I hope that P budget is less than budget, but we haven't written down that constraint. Maybe not. And then the sponsorship has a start date, has a since date. So they've been sponsoring this project since a particular date. Now let's think about employees. We're going to want to have some employees monitoring these projects. They're sort of the overseers of these projects that are sponsored by departments. So the employees have their social security number, their name, and their lot. They're going to monitor these things until they get to not have to monitor them anymore. Okay? But the question is, what is it that they're monitoring? They're not monitoring the project per se, because the project may have multiple departments sponsoring it. They're not monitoring the department, because there may be many departments involved. What they're really monitoring is this relationship between the project and the department, this sponsorship relationship. And remember that the sponsorship, there could be many sponsorships of a pair of projects and departments, because this is a many-to-many relationship. So we really want the employees to monitor that sponsorship. So we want to capture the sponsorship as an entity, and that's what aggregation lets us do. You can't have a diamond point to a diamond, because you can't have a relationship monitor a relationship. It has to monitor an entity. So what you do is you take this whole aggregation of the relationship and its associated entity sets, put a big box around that, treat that as an entity set. So you encapsulate not just the relationship sponsors, but all the things that go with it. Okay? And you do that by just encapsulating it with a dotted rectangle. And then that whole business can be treated as an entity set, in essence. Okay, so we would probably call this encapsulation. Since this was invented in the 1970s or something, they decided to call it aggregation. Be that as it may. Here's a different way to represent the same thing, which is a ternary relationship. Maybe it's the same thing, maybe it's not. All right. So rather than have monitors relationship set monitoring this aggregate, what if we had a monitors sponsors kind of super relationship thing that was a ternary between all of these? So we'd have employees, projects, departments. All right, and then this relationship between them would say that the employee, remember, is monitoring things until a certain date. The sponsorship is since a certain date. Okay? And all the other attributes are kind of the same. Is this the same information? Does this have the same constraints as the aggregation? How many people think they're equivalent? Raise your hand. How many people are pretty sure they're different? Raise your hand. And almost everybody either doesn't care or can't figure it out, which is not surprising the first time you see this stuff. It's a little maddening to worry about this. Like, at some level, you're like, who cares, right? And yet, when you write this stuff down, like, this is actually pretty important, particularly in environments where, like, the database is capturing business rules that have to do with things like federal compliance. So the federal government's going to come in and check your books and make sure that, every contract has, an underwriter or something like that, right? These are things like you have to get right for those reasons, these information models. They also may prevent your business from doing bad things like double billing or double booking or other things that like could lead you to get the numbers wrong. So they're pretty important, but they're very fussy. The nice thing is that actually at this level of abstraction, they're fairly clean, right? This does not just require a 20-line logic program to write down all the constraints that you might need, right? It's a very simple picture. It's easy to understand. But it is detail-oriented. There's no question about it. And it's not algorithmic. It doesn't do anything, right? Which I think is hard for engineers. It's a little hard for engineers to love because, like, it doesn't do anything. It doesn't go fast or slow. It's just a spec, right? It's just a logical specification of what's legal. Having said all that, it's still really important. Okay. So the thing on the left is different from the thing on the right. And what I'll do is make you think a little bit more situationally. So what might we change over time in one of these databases? What could change that we could capture in one schema but not in the other schema? Or we could or vice versa. Can anybody see something where things can change over time and the representation would be different in the different schemas? Or inequivalent? Yeah. So the hypothesis was that the thing on the left, let me see if I caught this right. The thing on the left has more flexibility, was I think what you said, in the way that monitors and sponsors can be combined.
The way that monitors can be allocated to monitors. Like in the right one, you have to have the same number of monitors for your projects and your departments. On the left one, you have like 2 per project and like 1 per.
Okay, so the hypothesis was it had something to do about the number of monitors for a project being more flexible in one place than the other. I'll point out that because all of these edges are thin ink and no arrows, these are all arbitrary many-to-many relationships. So we can have 0, 1, 2, or any number on any side of these edges, on any pairing, okay? Which means that on the right, you can have as many employees monitoring as many sponsorships as you want. So this thing, it seems to me, is the monitors relationship set can have as many many-to-many relationships on either side. And the sponsors one also can have as many many-to-manys as you want. Similarly here, it seems like the trio of employees, projects, and departments can be hooked up in many-to-many relationships as well. So there's no constraints on the cardinalities of these relationships in either case exactly. But you're getting at something, I think. Fundamentally, here there's 2 relationship sets, and here there's only 1, right? So there's something different. And what's going on over here is that monitoring and sponsoring are being bundled, and you can't decouple them, right? Somehow there's a decoupling of monitorship and sponsorship here. And if you look at the attributes, monitors here has an until clause, since has an until, sponsors has a since attribute, The until attribute and the since attribute can be kind of, you could have, and maybe this is what you're saying, but I think it's opposite. You can have until be a different number of things than since over here because the monitors and the sponsors are decoupled. Whereas here, for every until, there's a since, right? And so there's some number of monitoring is more flexible actually on the right per sponsorship than on the left. There have to be exactly as many monitors as sponsors on the left. But the number of monitors and sponsors can be different on the right. Does that make sense? So I think actually what you said, but the other way around. Yes?
On the table on the left,
The ER diagram on the left.
you can have a department-to-project relationship with multiple different SIDs because each SID is defined uniquely by the trio project department employee.
Mm-hmm.
You could have one monitor department project with the same department project, one SID state, and another employee monitoring that relationship with a different SID state.
That seems to be true on. Yes, interesting. So this is an argument for the point that was made before. So let's see on the left-hand side. Let's be very concrete. Let's put down names of employees, departments. Let's get this right. This is good. We're going to dwell on this for a minute. So on the left-hand side, let's have a project. It's called Jacobs Hall, which is that building going up next to Soda. That's the project. We're going to build Jacobs Hall. Okay? The department is going to be design. I forget exactly what the department's called, but it's a design institute. And the employee, to start with, we'll have an employee named Bob. And right now, what we're saying is that Bob is monitor sponsoring this since, January 1 until June 1. All right, hopefully that's unambiguous because until is after since. All right, now you're saying, I think, that we could also have in green. So let's do this. This is in black. In green, in that same thing, we could have build Jacobs Hall. Well, so we'll leave it black. But we're going to have a different edge here, which goes to Mary. It's going to have two different dates, right, for until and since. And it could still be the design department. Am I getting that right? That's fine. And your argument is we can't do that here?
So if each project department relationship is if it only occurs once in the sponsors table in between, then you can only have one since state.
Okay. We'll have Bob and we'll have Mary. So Bob can have a different until date. So the until, which in this case was 6-1, and the since was here was 1-1, right? Sorry, black. 1-1. Now your point is, let's do this again. What are you saying? Mary will have a different date here, right? What do we say? Mary didn't get a date. Let's give her concrete dates. Here, and this is, I think, your point. So she could be since 2-1 until 5-1. I don't know if you guys can read that, 2-1 and 5-1. So here, she can't have both of those things. She can only have until, which would be 5-1. And there's no way to capture in this schema the 2-1. Are we agreed on that? Because the lock-in on the project was 1-1. That's when it started being sponsored. But we could add an attribute to monitors, and then we could, right? And so it doesn't really require a change to the structure of the schema. It just says, well, gee, if what we mean by this date is both the date it started sponsored and the date it started monitoring, well, then put a since in monitoring, okay? And that's good. So this seems to be still more flexible. This could be 2-1. And in fact, note that here we could have the sponsorship start on 1-1 and the monitoring start on 2-1, and they're separated. And here we can't do that, right? So this is actually a bit more flexible than this one, all right? And maybe that's good, maybe that's bad, but it is more flexible. Okay, so you cannot capture the notion that sponsorship start and monitor start are different here. Here they're coupled. Okay. Thank you for working that through. And I think this is the kind of thing you want to work through at home as well. Yeah? Do sponsors have to be employees? Let's see. In this picture, no, sponsors has nothing to do with employees, actually, on the right-hand side. And that's sort of the point. On the left-hand side, employees are involved in sponsorship. And on the right-hand side, they're not. They're only involved in monitoring. Yep, right. If we took away the employees, the thing in the dotted lines would still make sense on the right, if you like. And on the left, the relationship is blown up, right? There's no definition of this ternary relationship without the employees. They're intrinsic to it. Yeah, it would be a different relationship if we took the employees away. That's another way to think about it, is that the connection between projects and departments is independent on the right of the employees. It's a very good question. Whereas on the left, the relationship between projects and departments involves the employees and would have a different meaning if you took the employees away. Great. Yes? Yeah. So, and let's be super duper clear. So, one more time with gusto. So let's see. Maybe I need to write down the names of all the attributes. Couple things going on the board that are maybe confusing. And why don't we do the following? Let's write down in a somewhat more tabular form what's going on here. So what we're going to say here is that, what do we know? Let's leave that there, and let's write over here. In black, which is to say the relationship set, the relationship on the left-hand side connecting Bill Jacobs Hall, Bob, and design. That's the black piece of information. Bill Jacob Hall is associated with Bob and the design school. All right, this is a fact. It's a relationship. It's not a relationship set. It's a relationship. All right, what else do we know about this relationship? It's got an until date of 6-1, we said. And it's got a since date of 1-1. So we've written it down in kind of a tabular form. This is the project. This is the employee. And this is the department, right? Good? Now, what we said about Mary was it's BJH all over again. But now it's Mary. It's design again. But with different until and since. So we said this was 5-1 and this was 2-1. Okay? That's what we drew on this. So this all relates to the ternary relationship example. Now we can do the two binary relationship examples separately. Okay? Here we're going to have a project, an EMP, a department, and until that's associated with the sponsorship, and an until that's associated with the monitors, and a sponsor since date. Okay? And we started with Bob, or BJH, Bill Jacobs Hall, Bob, design, 6-1, sponsor since 1-1. Okay? And then we had Bill Jacob Hall with Mary, design. Now the since has to be the same. on the right-hand side picture because it's the same sponsorship that we're talking about. But the until can change for Mary. And what we said was if we want Mary's monitoring to have a since date, monitor since, we could add that to the monitors relationship set. That would be fine, but it would be sort of different. It would be monitor since. And then if we wanted Mary to have different dates than Bob, that could be fine. In fact, they could both have different dates. This could be 2-1, and this could be 3-1, and that would just be different information. Right? But here, the until and the since go together 1-to-1, and here they're decoupled. Monitor until, sponsor since. Okay? Now, what we're going to do in a few slides, and maybe we'll take a break before we do that, is we're going to show you how to translate ER diagrams to SQL. And I've elided a little bit here the details of what the tables are and how they're joined together. All right? And what you're going to see when you convert the thing on the left and the thing on the right to SQL is you get different table structures with different keys and foreign keys that will enforce these constraints. But the thing to keep in mind here is that the sponsorship relationship over here is independent of the monitors, and here they're coupled. I mean, it's pretty much that simple. Okay. So, as we saw, entity relationship modeling can get tricky, right? This whole idea of conceptual modeling is not sort of as easy as it seems. We started with boxes and arrows, and it seemed just fine, but it actually gets pretty subtle, okay? So some of the design choices you'll end up thinking about, and we'll talk through some of these over the next slides. Should something actually be an entity, or is it just an attribute? Should it be an entity, or should it be a relationship? Actually, sometimes that's ambiguous. You can think about an insurance policy. Is that a relationship, or is that an entity set? And for relationships, are they binary? Are they ternary? When do you use aggregation? Okay? So this stuff all requires careful thinking usually about duplication of relationships and whether attributes can be associated with one or more things. All right, the goal of this whole business is that you want to capture as much of the semantics of the real world as possible. You want your database, if this is one of these governed systems that's running your bank or running your business, you want it to capture what's possible in the real world and forbid what's not. Right? You don't want people to pay 0 or more times for an item. You want them to pay exactly once for an item. Right? You want to capture this stuff correctly. You can try to capture it in application logic. You can put a bunch of if statements into your Java code. They will encode the same information as we're writing down here, okay? Except that they'll be scattered through your Java code, and it'll be really horrible to think about them. If you capture them in your data model, they'll be enforced in one place, down at the storage layer, and you'll think about them holistically when you're designing your application, which is a good time to think about them, if you're doing one of these carefully designed, long-lived applications. Now, some constraints cannot be captured in the entity relationship model because it's just not that rich and expressive language. There's things you can't say here. You can't say your bank account must be greater than 0 because it just doesn't do numeric constraints, for example. And you certainly can't say the sum of checking and savings must be greater than 0. All right, so simple examples like that. But you also can't say things like, we can only allow 350 students in CS 186 because it can't count either. It's not just about arithmetic. There's a whole bunch of things you can't say here. So we'll have to refine the constraints and add further things when we get down to the relational level. All right, so just keep that in mind. But what we're going to do next is go through these red choices and get a little bit of a rubric around how to think them through, one at a time. So first off, entities versus attributes. Okay, so address. Should address be an attribute of employees, or should it be an entity of its own? This is a fine example because it depends. It depends both on semantics and on usage, all right? So first of all, there's a question of the number of duplicates, the number of variants. It's not duplicates, it's sort of the many-to-one kind of argument. So if you have multiple addresses for an employee, they have their home address and their work address, or they have their vacation home and their regular home, it needs to be an entity. And that's because the ER model, like the relational model, says that attributes are atomic values. They're things like an integer or a string. You're not allowed to put 2 addresses into the address attribute. Okay, so if you have 2 addresses associated with somebody, that's a relationship between a person and addresses. And that means address is now an entity set, and the relationship is lives at, or something like that. So if you have several addresses for employees, it must be an entity. And then the other thing is that an attribute is atomic not only in that there can only be one copy of it, but that you can't break it down any further into fields. So an attribute can't be a collection type, including it can't be a tuple type, which means that If you care about like breaking an address into a city, a street, a zip code, and so on, then again, you want it to be an entity and have those pieces of the attribute be attributes of in and of themselves. Okay? So sometimes it's fine to leave things as attributes. Sometimes they deserve to be entities. Here's an example of our works-in relationship. We're going to look at a couple variants. So in works-in 2 at the top, an employee cannot work in a department for greater than 1 period here, it says in works-in 2. Employee cannot... not work in a department for greater than 1... Gee, I looked at these and now I can't make sense of it again. I apologize. Yeah, okay. In the first one, an employee cannot work in a particular department. Bob cannot work in the shoe department twice. The relationship, not the relationship set, but the relationship between Bob and the shoe department, those two entities, has exactly one works in 2, which is the time that Bob worked in that shoe department. Now, Bob can work in lots of departments, and the shoe department can have lots of employees. But Bob in the shoe department happens exactly once with a from to date. If it's the kind of thing where Bob worked in the shoe department, then later he went to the toy department, and then he came back to the shoe department, we would need something like works in 3, where there's a ternary relationship between employees' departments and the duration they were there. And those durations can be many different spans. So now Bob, shoe, and multiple durations can all be associated. Okay? So this is a case, the reason I had to think for a minute was the thing at the top is many to many. It seems very flexible on a relationship set basis. Bob can work in many departments. Each department can have many employees. Okay? But for a given relationship, Bob and shoe, it appears at exactly once, right? And therefore can have only one set of attributes associated with it. Yes? Again, so let's be careful. The difference, and this is why I had to think also, so I'm glad you're making me reiterate. The difference between many to many, many to one, and all that has to do with relationship sets. Remember that picture that we had previously where we drew those obvious sort of simple set relationships with bipartite sets, right? You have a drawing like this and a drawing like this, and each oval represents a relationship set. So this is employees, and this is departments. Each employee can work in many departments. Each department could have multiple employees. Agreed? Okay? But if this is Bob and this is shoe, there's no notion that there's multiple edges between Bob and shoe. So the relationship, not the relationship set, but the relationship between Bob and shoe is just one. And the attributes associated with it, from and to, are unique. If we want there to be many sort of edges between Bob and shoe, we need to introduce a third oval. So let's do it all over again. Here's emp. Here's dept. And here's work. Here's, what do we call it? Duration. And now we can have Bob. And we can have shoe. And we can have 2 different times that Bob worked in the shoe department. There's 2 paths between these nodes, right, that are distinct. Right? So if you think about it, these are sets, and they are many to many. They're all many to many in principle. So this could point multiple places. This could point multiple places. This could point multiple places. This could point multiple places, I guess, although that seems crazy. This probably should be written down. But the point is that for any individual path, that's an association between entities. It's a relationship, not a relationship set, and that's unique. Every path through these things is unique. Does that make sense? Right? And the attributes are hanging off of these edges. They're not hanging off of the sets. All right, so this is in some sense the same idea as having multiple addresses per employee. Multiple durations per employee is a similar issue. It's just that it's associated with the relationship set as opposed to with the Hello? Yeah, okay, good. I'll put this down. I'll pick this up. All right, here's a different situation. We're going to have a separate discretionary budget for every department. All right? Right now, departments have a budget, and the management relation, each department has participation in at most one manages relationship, right? Because there's key constraint from departments to managers. So there's at most one employee managing the department, and that management relationship is associated with a discretionary budget. So that's cool. But what if the manager's budget was like they had the ability to spend that budget across all the departments they manage? So I manage the computer science department, and I manage the statistics department. I'm the lord of all data, okay? And I should get to choose, that CS gets more money than stat, because that's what I want. I don't want the university telling me exactly what my discretionary budget is for CS and stat. I want a slush fund. I like my slush fund. I can't capture that in the schema up above because the D budget is associated with my management of CS, and it's separately associated with my management of stat. I want my slush fund. So for my slush fund, I need a new design. All right? So this is one where now, rather than managers being a relationship, I want my appointment as a manager to be an entity set. All right? And then my slush fund goes on Joe the manager appointment. All right? When I get appointed, I get a slush fund. And I get to spend it across the different departments that I manage. Okay? And in principle, the different employees that manage these departments. Okay? But notice that employees and manager appointments are now in at least one relationship in both directions. Each employee manages, that seems a little weird, actually. Each employee manages at most one department. Sorry, each employee has at most one manager appointment. Thank you. Okay. The arrow coming from the top down says each employee has at most one appointment as a manager. I can't be appointed a manager twice because then I'd get 2 slush funds. That doesn't seem right. Okay? That's what the arrow coming down is. The arrow going up says that each manager appointment has at most one employee associated with it. That slush fund belongs to at most one person. Okay. And then in this direction, every department has at most one manager appointment associated with it. Yes, question. Great question. The question is, why can't we, to get the semantics we want at the top, why not put the D budget on the employee? That was the problem, right, is that Joe wanted to have his own budget. So why not put the budget on the employees? Anybody have an answer to that? Then everybody gets a slush fund, even if they're not a manager. Okay? Which, maybe that's fine because it's 0. But it's a different representation. Yeah? So here, D budgets are only associated with management in both cases. You don't want the rank and file to have budgets. All right, good. But you see these little design decisions, right? They all have implications. Okay, now if you like this stuff, I encourage you to paper your wall with it, right? Because this is what happens when you do a really big design for a really big system. This is I took this off Wikipedia. I Googled for big ER diagram. So these aren't that hard to find. They're pretty typical. If you get a job at McKinsey or one of these places out of college, that might be your job, is to generate this kind of stuff. All right. It's not surprising because when you get into a business and you really start paying attention to what all goes on when people shop at Amazon, really, there's a lot of stuff going on back there. It's not just you and your shopping cart. There's all the suppliers. There's all the credit card approvers. There's goodness knows what. There's just a million things to be captured to represent a big enterprise, right? And if you want to capture it right, and there's a part of Amazon that wants to make sure all the billing is right and all the numbers are right. It's not all just scale. A lot of it is get the rules right. You get stuff like that. So just realize that this stuff gets pretty complicated in reality, and we're really zooming in tight on the details here. Okay? So let's take a little break. We got 20 minutes left. Let's take a couple minutes to stretch because the next thing is technical. We're going to convert these ER diagrams to SQL. All right. So a little side chat I just had with the TAs apropos of homework 3. So we said after homework 1 and before homework 2 that submission errors, that is, you didn't submit the project through GitHub correctly, would be shown no mercy. And yet, we have found that many people unsuccessfully submitted homework 2. So there will be something less than complete mercy for such people. And we were debating about what's fair there. But you will certainly be docked points on homework 2 if you did not submit correctly. That applies all the more so to homework 3. In fact, I'm tempted to say that the penalties will go up as the projects go forward. So, if you mess up on homework 2 in the submission, we may dock you some points. If you mess up on homework 3 in the submission, all right, we've already appealed to you twice now. And the reason for doing this has everything to do with the fact that we have 300-odd students in this class, and there should be some penalty for not following instructions because we can't scale the exception handling with the size of the class, right? The TAs can't exception handle you not following instructions. So there will be some penalties.
So when we submit to the auto grader, we get emails. But when you submit to a release thread, we don't get emails. Is it possible you could get a confirmation that our project has been submitted successfully?
Your confirmation should be going into GitHub, go to the release homework 2 branch and that's how GitHub UIs. The auto-grader email is there to confirm that whatever you've done runs successfully in our environment. Okay. It's not like a submission confirmation. It's that your code actually works in our environment.
Okay, I'm not going to repeat that for the benefit of YouTube because it was sort of a question was asked and I think no change resulted from the question. So everything is as it should be. That's, I think, the upshot from that. Okay, so moving on, we'll start talking now about converting entity relationship constraints to relational database constraints, or entity relationship schemas to relational schemas. Really, I'm sure you could see through this. This feels a lot like tables. We even tried to draw them as tables. And I went through this, and you saw I used 2 different colors for encodings to try to capture that there's some variation going on. It's not like this whole business turns into one table, right? There's something complicated going on, and we felt that when we were trying to feel our way through these examples. Let's make that very concrete now. All right? How do entity relationship diagrams and their constraints get captured by relational tables and their constraints? Okay? And it starts out dead simple. Entity set is a table. The key of the entity set is the key of the table. Right? So here we go. Entity sets, employees, social security number is the key. There's the SQL, okay? Social security number, name, lot, primary key, social security number. It's that simple. All right, so that's fine. Keep an eye on that. Let's not forget our keys. Okay, what about relationship sets? Well, if everything's easy, if it's many to many, it's pretty simple. We're going to create a table for the relationship set. So like works in, all right? And what does this table have to have? It has to have the keys of the entities that it's connecting, right? So the works in relation has to talk about an employee and a department. So it'll have the key of the employees table and the key of the departments table, social security number and department ID. It will also have whatever attributes that the relationship set had, like since, okay? Now note that the social security number and the department ID, which is to say the keys of the relationship sets that it's connecting up, together form a superkey for this table. So we're going to say primary key SSN DID. Not only is it a superkey, but it is the key in this example. Okay, the key for this relationship set is the keys of the 2 entity sets it connects, right? Because it's exactly this conversation we had before. Each one of these edges is a unique relationship between an entity and an entity. Right? So when we write them down in the relationship set table, each row in that table corresponds to an edge in this picture. Okay? And there can only be one edge between any 2 dots. Okay? And then, of course, these are foreign keys. SSN is a foreign key to employees, and departments is a foreign key to, DID is a foreign key to departments. Again, this is pretty straightforward from many to many. Now let's think about our constraints. Remember this picture. In this example, we have a key constraint. Each department is managed by at most 1 employee. Right, how do we capture that in SQL? And remember, one-to-one, one-to-many, many-to-one, many-to-many. Well, there's actually two ways to do it. So let's look at the left-hand side first. Okay? So what we're going to say is in this manages table, remember that the primary key for many-to-many in the previous one, the primary key of this relationship set was the two foreign keys, was SSN and DID, right? Works in. SSN DID captures one of those edges. Now look at this one. Left-hand side. The primary key of manages is just the department ID. It's just the department ID. What's that about? What happened to the employee? Why isn't Social Security number part of the primary key here? Yeah. All right. Only one employee is going to be managing a department. So what was said for those of you on TV was there's no point having the SSN in the key because there's only one SSN associated with the department. Is somebody want to say something just slightly stronger than that? It would actually be bad to have the SSN. Excuse me. It's not just that there's no point. It's actually bad because if the SSN was part of the primary key, what could you have? You could have one row with SSN1 and department shoe, and you could have one row with SSN2 in department shoe. And that would mean you have two managers for that department, right? By having only the primary key be DID, that means that the managers relationship can have at most one row per department, which means it can have at most one manager per department. So that removing SSN from the primary key enforces the at most one constraint. That's exactly how we capture it in SQL, is we take the foreign key to employees out of the primary key of manages. Smaller primary key, less flexibility. Fewer columns in the primary key, less flexibility. All right? Here's another way to do it on the right-hand side, which is don't create a manages table at all. Just stick the manager information on the department. So we'll create a depth manager table that captures both the department and the management information. Because after all, there's only at most one manager per department. So we can have the manager information be kind of a decoration on that department, just extra columns. All right, so that table, depth manager, will have the department ID, all the department attributes, DNAME and budget, and it'll have the manager as an attribute, SSN. It's just an attribute of the department, there's a manager SSN. Okay? And a since date, which came from that manager's relationship set, will also be part of the department information. The primary key is still DID, because there's one row per department. There is a foreign key on employees to SSN. Okay? Oh, by the way, it would be just fine to have the SSN and since fields be null. Nothing in the schema says they can't be null. So there can be departments with no managers, which we want because that's what the ER diagram says also. It says at most one. It doesn't say 0 is forbidden. All right, so 0 is allowed here too by putting nulls into the SSN and since. Good? Okay, now let's look at participation constraints. All right, we want every department to have a manager. So before, every department had at most one manager. In this picture, every department has exactly one manager. What changed? Here's our same department manager table as on the right. See that? Primary key DID, foreign key SSN. Look at this one. Primary key DID, foreign key SSN. That's all the same. What changed? Did anybody see the diff between the previous schema definition and this one? SSN, not null. That's the only difference. Right here, you're not allowed to have a department have a null manager SSN. You have to specify the manager. Okay? You can't insert a tuple into this where SSN is null. And that enforces the participation. At least one. Okay? And in fact, exactly one. Because there's only one department ID entry in this table. All right? There's a little bit of extra syntax here, which I believe you learned from Professor Franklin while I was gone. On delete, no action. What that means is if you try to delete the foreign key here, you try to delete someone who manages a department, that's forbidden. That transaction will abort and be rolled back because that person's a manager and their department needs them. And we said so. So they cannot be deleted. Can't be fired if you're a manager in this scheme. Okay? That's pretty cool. But that's what that says, all right? We could have written it differently. We could have said on delete cascade, which would have meant if your manager is fired, then all the employees are fired as well. And that would also enforce the integrity constraint, all right, but in a somewhat crueler way. So that's the key to this thing. All right, what about weak entities? How are we going to do this? Well, I should make one more point. This thing worked. This trick with depth manager and not null worked because it was a binary relationship with one participation constraint on one side, right? If you go back to the picture, like that, notice that the manager's relationship has a dark edge on it, but it's only got a dark edge on one side, and it's a binary relationship. So we can take departments and managers and smash them together into one relational table, and it's all good. But if it was a ternary relationship, or if there were dark edges on both sides, let's do dark edges on both sides first, then would managers go to the right or to the left? It can't go to both, and then we're stuck. All right, so you can't play this trick of mashing together the entity set and the relationship set into one table if there's dark edges on both sides of the relationship set. So it's a bit of a special case. In ternary relationships, same problem. You don't know which way to go. So it's a special case. And this won't work otherwise. And the other way you enforce this is by having some constraints hanging out in the breeze. So I don't know if Franklin talked about this, but there's the idea of a check constraint in SQL, where you can say create constraint, check, arbitrary query is empty. You can write anything you want in there, okay? So some constraints, if you can't capture them in the schema definitions, you can just write them down. So you could say things like, the number of students times the number of professors divided by pi can be no smaller than 6.3. You can just write that down as a check constraint. Similarly, you can write down check constraints like this, where you say, every department has to have exactly one manager. Every manager has to manage exactly one department, stuff like that. And you can have both sides of a relationship have participation constraints. But you're going to have to write that down as a separate check. So there's no trick to do it with keys and foreign keys. The problem with check constraints is they're extremely expensive to enforce because every time you change any table that's mentioned in the check constraint, you have to run the query in the check constraint and check it. Right? This stuff you can enforce. Keys and foreign keys are easy to enforce. You can do it with a B tree. If there's a B tree on the key attribute, you just make sure to walk down it when you need to check things. Okay? So arbitrary check constraints are a bummer. But you can always write them down if you need to. Okay. Weak entities. Here's our example. Remember, we have dependents that are weak entities on insurance policies for employees. So the employee is the key, and the weak entity has a partial key called pname. Remember my daughter Dahlia? Okay, so we can take that weak entity set and the relationship set because it's a bolded thing on only one side of a relationship, just like we talked about. We're going to smash together dependents and policy into one table, and it's all going to work out just fine. So here's how it looks. Dependent policy. You got your partial key pname, but the foreign key to employees is the rest of the key for that partial entity, right? So Dahlia, the name Dahlia is in pname, and my social security number is in SSN because it's pointing at my record in the employees table. And that's a unique identifier for my daughter Dahlia. She is Dahlia, the daughter of my social security number, right? And she's got an age and a cost and all that stuff. And the primary key here is the pname and the SSN. And here, on delete cascade probably makes sense. If I get fired, sadly, Dahlia will no longer have insurance coverage. But that's probably what they intend, right? Right? They probably don't intend anyone who has children can never be fired. That's kind of nice. It's a little socialist. It's kind of got some pros and cons. Doesn't incent me to do, work real hard, whatever. You can decide how you feel about that moralistically. Okay. All right. Well, that's a bunch of stuff. I will point out that a tool like ERWin, you draw all your boxes and arrows, and you get your bolds and all that ready, and then you say translate to SQL, and it goes, and it generates you a whole bunch of create table statements, and you're done. So all this stuff can be made completely automatic. This is a totally deterministic translation from ER diagrams to SQL, and I would expect you guys to be able to execute these translations for the cases we've looked at, certainly, in the slides. All right, we've covered most of them. We've covered participation constraints, key constraints, weak entities. We did not talk about how to translate aggregations, but it's pretty straightforward and obvious, and you should see how to do it. Okay. And I think that's everything we talked about pretty much. So ternary relationships, maybe we didn't write down either, but if they're many-to-many, it's completely straightforward. So you should be able to do this yourself. And it's kind of nice. What this means, backing out of all the what's on your test, is that people can live in this pretty graphical world, and they can compile it down to MySQL, or frankly, they can compile it down to weird JSON in MongoDB and never be any of the wiser if that's the way you want to live. Okay, MongoDB is not going to enforce as many constraints for you probably as MySQL, but certain constraints can be enforced by nesting your documents, right? We won't talk about that so much. The point is, the ER model is at some level a higher conceptual plane than SQL and Mongo and all these things. And for conceptual design, maybe that's good, right? Because you can put it on the wall as a McKinsey consultant and talk to your client about it, and your client will understand what you mean. You can walk them through it and point at things, right? So that's good. So it's a high-level language that can be compiled down to a low-level language. So this conceptual design, popping all the way back out, comes after requirements analysis. First, you talk to your customer and you say, I see that you want to start an online betting site. That's cool. What's involved in an online betting site, really? And they say, whatever. There's like events and bids and customers. And you just go make it. And you're like, okay, events, bids, customers. Is there anything else? And you sort of have that conversation for a while. And then you go out and you draw a schema and you're like, well, can a person put 2 bids on an event or not? And then you have to go back to the customer and say, well, what do you think? And then you can go back and forth. But you do that now at the conceptual design level, right? And you have this nice graphical environment to talk to them about their scenario, all right? And when you're done with this, that's awesome. And you can compile it down to SQL, and you've locked in your integrity constraints. Very good. Maybe you don't want to do that if you're in a little bit more of a loosey-goosey setting. So you're not actually designing a commerce site. You're actually trying to just come up with something that you're going to do analytics on. Maybe then you do something more sloppy and do schema on use. And I want you to understand that all the stuff we talked about right now is really for when you want to lock down a design, right? Okay. The ER model is a popular way to talk about conceptual design. It's pretty expressive. It's pretty close to the way people think about their applications, actually. It's not so different from the kinds of models that you build in an object relational mapping tool like Ruby on Rails or Django or Angular or one of those things. The models you have in those applications tend to look very much like these ER diagrams, and for good reason. This is kind of application-level thinking, all right? There are many variations on it. So, you get into little subtleties about, well, Rails calls it this and this calls it that, but don't worry about that so much. They're all kind of the same, and now you've seen them. Basic constructs in the ER model, entities, relationships, and attributes, which are assigned to both entities and relationships. And we taught you about weak entities. We talked to you about aggregation. We did not talk to you about ISA hierarchies, which is roughly the ER equivalent of inheritance in type systems. All right, we didn't talk about that. I won't make you responsible for it. If you're curious, you can see the book. It's not really all that exciting. But those are some of the concepts that are in the book. All right, in terms of integrity constraints, you should understand the ones we can say in the ER model. So key constraints and participation constraints. Implicitly, as we saw, some foreign key constraints are kind of there in the definition of relationship sets. The definition of relationship sets, and you should understand that translation. But there's many other constraints, one of which we'll talk about a lot is functional dependencies that you can't express here and you need to do in schema refinement, which is the next phase down the pipeline. All right, and these constraints, as we said, play an important role in determining the best database design for the enterprise. To get your rules right for whatever it is you're building. And if you don't want to think about commerce, maybe you want to think about something more important like medical records. Every patient should have a case number. Every patient should get treated, all that good stuff, right? So it's not all about making money. Okay. It's a subjective thing. Should an online betting site allow you to bet twice on the same race? I don't know. It depends. Changes the rules. If you get to bet twice, maybe the incentive structure is different. Maybe it's a different kind of betting. I don't know. So it's subjective. There's many different ways to model a given scenario. They lead to different meaning. All right? And analyzing the alternatives can indeed be tricky in these complicated scenarios, and you guys should have some appreciation for that coming out of here. I think a lot of people poo-poo this stuff as being boring. You just draw boxes and arrows, blah, blah. It's actually a little bit subtle. And so thinking about these things like entities, attributes, entities versus relationships, is it binary, is it n-ary, et cetera, this takes some thought and gets you digging in deep with what should be allowed and disallowed in the world we're trying to model. Okay, but that's not enough, actually, so the resulting relational schema we'll see can be analyzed and refined quite a bit further. This functional dependency information and the notion of normalization are what we'll talk about next. All right, it is Thursday. Next Thursday there is a midterm. Tomorrow there's a homework due. Good luck. I will see you next Tuesday. Bye.